Okay, let's start. I am Pharma Omics. Today's lecture I will tell you about LFQ intensity, fast LFQ, LFQ mean number of neighbors, and LFQ average number of neighbors. Before I will explain the label-free quantification in MaxQuant, I will explain the difference between label-based quantification and label-free quantification. A label-based quantification. In this approach, the proteins in the sample are chemically labeled with different isotopes, such as heavy and light nitrogen. It contains Scilab and TMT. Label-free quantification. In this approach, the proteins in the sample are not chemically labeled. Instead, the abundance of each protein is determined by comparing the signal intensities of the protein's peptide after they have been separated by mass spectrometry. I will explain the abstract of label-free quantification in MaxQuant. Label-free quantification in MaxQuant takes two steps for determining relative abundance of protein: normalization and quantification. Normalization: the signal intensities are normalized to account for differences in sample preparation and instrument performance. Quantification: fold change in the abundance of each peptide between two samples are used to extract much information for quantification. First, let's look at normalization step. In MaxQuant LFQ, the reason why doing normalization is to minimize bias which occurred in sample preparation or LCMS step. Before raw data processing in MaxQuant, there are many steps to affect the accuracy of sample abundance result. For example, there are sample preparation step and LCMS step. First, sample preparation bias can occur in several ways. For example, protein concentration determination using BSA or nanodrop, and digestion or sample fractionation step introduce variability in the protein recovery, leading to biased result. And a bias in LCMS step can arise from various sources such as status of column and sensitivity of mass spectrometry. So normalization step is used to correct bias for quantification of proteins. Normalization factors in MaxQuant LFQ are used to adjust the peptide or protein intensities across different samples to account for bias. For example, there are three samples A, B, C, and each sample have two fractions. Each fraction in individual samples have two peptide XIC intensity, peptide X and peptide Y. Also, each fraction in individual samples has normalization factor. Fraction and sample information is denoted by subscript. Principle to get intensity is simple. Before sum of peptide XIC in each fraction, normalization factor n should be multiplied. Let's calculate intensity of peptide X in sample A. Sample A has two fractions, fraction 1 and fraction 2. Each fraction has peptide X XIC and peptide Y XIC. First, XIC of peptide X in sample A1 should be multiplied by normalization factor A1. And XIC of peptide X in sample A2 should be multiplied by normalization factor A2. and add them together. And do same for the other intensities. And calculate the pairwise fold changes with the corrected values by normalization factor. To get pairwise fold changes, peptide intensity in sample A is denominator and sample B is numerator. And then fold changes are logarithmized and squared and summed. In our case, for peptide X fold changes between sample A and sample B, and sample A and sample C, and sample B and sample C is logarithmized and squared and summed. Then we get Hn for each peptide. The resulting value Hn for all peptide ions are summed to calculate the total quantity Hn. And our purpose is to minimize Hn. Let's look at fold change between each samples. If fold change values go to 1, Hn gets smaller, as log 1 is 0. If we minimize Hn, overall fold change will go toward being 1, meaning that the overall peptide intensity between samples is similar. Okay, now let's look at real MaxQuant program. If you click Label-Free Quantification tab, there are many parameters to choose. LFQ mean ratio count will be discussed next video. Today we will look at normalization type and best LFQ. Normalization type is very easy. There are two options, none or classic. If you choose none, normalization step is skipped and only quantification step is processed. If you choose classic, the normalization algorithm will be processed before quantification step. It's easy, right? Fast LFQ is designed to provide fast and accurate quantification of proteins. It is optimized for speed and can process large data sets quickly. How can fast LFQ reduce computational cost? In calculating Hn for each peptide step, pairwise fold changes between samples are used. The number of time you need to calculate the fold change is the number of combination of selecting two samples from total samples. So, fast LFQ is using only subset of combination of samples, making reduced computing time. Note that if the number of samples is below 10, original normalization algorithm will be used instead of fast LFQ. And next parameter is to select number of neighbors. This part I didn't fully understood. I will explain what I understood until now. I will recommend you to read the MaxQuant LFQ paper. For example, we have 5 samples A, B, C, D, F. Samples with similar peptides to each other will be close together and are called neighbors. And the samples that are neighbors are calculated for fold changes. I think number of neighbors is the number of fold changes to make based on each sample. If minimal number of neighbors is 3, every sample should be calculated for pairwise fold change at least 3 times with their neighbors. And if average number of neighbors is 6, average number of pairwise combination fold change is 6 with their neighbors. In summary, there are two steps for calculating LFQ intensity: normalization and quantification. Normalization involves calculating normalization factor for each sample to correct bias occurred in sample preparation and LCMS steps. Fast LFQ can reduce the computing cost by using only meaningful subset of pairwise uh, combination of samples. Quantification step is explained in the next video. Okay, thank you for watching. See you next video.